Okay, we'll look at this first example with sample means. It says, suppose the mean annual cost of automobile insurance is $939 and the population standard deviation is 245. What is the probability that a simple random sample of automobile insurance policies will have a sample mean within $25 of the population mean if the sample size is 30? Okay, a key word here in this is sample. We're taking samples. So we know that if we have a sample size of at least 30, the sampling distribution is approximately normal. Now remember that the sampling distribution is the distribution of all the sample averages that we would obtain from taking samples of size 30. And this population being quite large, there's almost uncountable number of samples of size 30 that we could take. But if I took the averages from each one of those samples and put them into a histogram, it would be mound shaped. We could apply the normal distribution density function to model this, and we understand that the average of all the sample averages would be the population average, and that is given to us as $939. But the standard deviation of the sampling distribution, and that would be calculated by taking the standard deviation of the population, which we were given, and dividing it by the square root of the sample size, and in this case 30. So I would get 245 divided by the square root of 30, and that would be 44.73. Now, to use the standard normal table, we need to know that the distribution is normal, and we know that from the central limit theorem. We also need to know the mean, and the mean is the population mean, 939, and we need the standard deviation. And this is the sampling distribution. Central limit theorem also provides that. The standard deviation of the sampling distribution is standard error, and that would be 44.73. Now, what I need is the probability that the simple random sample will provide a sample mean within $25 of the population mean. So I'm going to take 939 and I'm going to add 25 to it, and I'm going to subtract 25 from it. So that means that I would be about right here and here. Standard deviation of the sampling distribution is about 45, so 25 is about a half a standard deviation. So I've got 914 to 964. So I've got to find the probability that my sample average would fall in that interval. So the probability that the X bar sample average would be between 914 and $964. Again, to find that probability, I need to find the area under the density function above that interval. And I also realize I have symmetry here, right down through the center where the average is. And knowing how to use a standard normal table, that I would be able to use the table to find the area from the center out to, in this case, the z value of 964. Also, since I'm $25 on each side of that, in other words, the same distance, by symmetry, this area to the left of the center out down to the 914 would also be the same area. But to go to the standard normal table, I have to translate this into a z-score. So I'm going to find the z-score of 964. So 964, subtract the mean divided by the standard deviation. And I get 964 subtract 939. And then divide that total by 44.73. So I get a 0.559, which I'm going to, the table only goes out to hundredths, so that is 0.56. I'm going to look up a 0.56 in the standard normal table. 0.56 in the standard normal table. So Z is 0.56. There's my 0.5 row, and then I'm going to go down to column 06, 0.2123. So this area to the right from the center is 0.2123. Now, I have symmetry on both sides of that, so the left side is 0.2123. So I would write the probability that X bar is between 914 and 964 is the probability that Z is between a negative 0.56 and a positive 0.56. So that would be 2 times 0.2123. So that would be 0.4246, or 42.46% would be my answer. The probability that if I would take a sample of size 30 and I'd calculate the average on that sample, the probability that that sample average would be somewhere between 914 and 964 would be 42.46%. Or I could say 42.46% of the sample averages will be within $25 of 939. Okay, we're ready for part B. What is the probability that a simple random sample of automobile insurance policies will have a sample mean within $25 of the population mean, but this time if the sample size is 400? And a rough sketch of the sampling distribution. And in this case, again, there's the expected value of the sample average is the population average, $939. Our standard error is going to change. That's the standard deviation of the sampling distribution of the sample averages. And that's the population standard deviation divided by the square root of the sample size. And the sample size is quite a bit larger this time, which brings the standard error down from 44.73 to 12.25. So we're still within $25, but $25 is almost 2 standard deviations. So my 914 moves out to about down here, and my 964. So my interval here is a bigger part of where the sample averages are. So the probability that X bar will be between 914 and 964 is equal to the probability that Z, now what is our Z score for the 964? We subtract 939 again, but this time dividing by 1225. And that is, yeah, right about 2 standard deviations, 2.04 standard deviations from the mean. My sample of size 400 would produce a sample average within that interval. Again, is the area under the density function above the interval. But this is a lot larger part of the total area. So we would take, this time, 2.04 to our standard normal table. And 2.04, there's 2.0, and then column 04. So we have 0.4793. 0.4793. So this would be the area from the center out to the Z. And again, because we are $25, in this case, from the center on each side, we do have symmetry. And this side we could also say is 0.4793. So the probability that X bar is between 914 and 964 is the probability that Z is between a negative 2.04 standard deviations to the left, which is the 914, and positive 2.04 standard deviations to the right of the average, which is 964. And that's going to be 2 times 0.4793, which equals 0.9586, or 95.86%. Now, let's compare the results from Part A, where we took a sample of size 30. We were trying to find the probability that X bar was within $25 of the population average 939, or somewhere between 914 and 964. That probability turned out to be 42.46%. But in part B, when we changed our sample size to 400, the answer to the same question, the probability that X bar is within $25, or between 914 and 964, turned out to be 95.86%. And that makes sense because the bigger the sample, the more accurate the result would be. So I'm more likely to be within $25 of the real population average than I was when I only had a sample size 30.